we have to have a look at distillation and fractional distillation. People, we use distillation or fractional distillation to separate substances that have, yeah, there is sound. To separate substances that have different boiling points. Or, if, for example, we had a look at an example yesterday of crystallization, where we had a mixture of salt, say for argument's sake, dissolved in water. Then you can evaporate off the water and you are left with table salt. But let's say you're not interested in the table salt as such, you want the water. Then you would be able to do a distillation to remove the liquid part from something that is dissolved in it. Okay. Now, distillation simply works on the basis of, if you have substances with different boiling points, you can boil off the one substance with the lowest boiling point first, and you can condense it, and you can catch it up, and then you can get the next one with the higher boiling point. Now, this only works very well if the boiling points differ with about 50 degrees Celsius. Okay, so, well, with liquids of which the boiling point differs with about 50 degrees. Okay, now we use an apparatus, this thing over here, called a Liebig condenser. Over here, that part there is a Liebig condenser. Now, it's a simple process. You will take your mixture and you will heat it up. You'll have a thermometer so that you will know what temperature this mixture is at, so that you can control the heat of the flame so that only the first substance vaporizes. So the vapor rises up, okay, and it goes down this tube there, okay. But now circulating around this inner tube over here, we have water. The water goes in there, it circulates around the tube over here. All right, remember this is a flat diagram. It's a three-dimensional structure. It's a tube with a tube in it. And the water circulates around this gray part. No? Okay, so it cools down the vapor and it condenses, and the condensate is caught up in a container. All right. What is important with the Liebig condenser is that you must remember that the cold water goes in at the bottom, so and the warmer water will come out at the top, so that we find there's an exchange of heat. As the warm vapor comes down the tube, the cold water is circulated in the opposite direction. And it allows for a longer time of contact with fresh cold water to exchange the heat effectively. So always cold water in on the bottom, the warmer water is circulated out on the top. Note the other apparatus. Here I have a retort stand with a clamp. There's my retort stand. There. There's my clamp. What would the name of this container be? That one would be what type of flask? A round-bottomed flask. No, it's got a round bottom, so that's a round-bottomed flask. Got the Bunsen burner and a thermometer. Now, sometimes we have more than one liquid in a mixture, and their boiling points are slightly closer together. All right? Then we do a process called fractional distillation. And to do fractional distillation, we add a long column on top of the flask. Over here, can you see we just had the thermometer in it? By fractional distillation, we extend the neck of the flask with a long column, and usually inside that column, we find something like glass beads. All right, and all that happens is, as the liquids vaporize, they rise up. But as they rise up, they start cooling. All right, but the one with the lowest boiling point, will be able to go up the highest before it condenses. So we find that if you maintain the temperature, say there's a liquid that has to vaporize at 40 degrees, you maintain the temperature at 40 degrees, the vapor will rise up. But if there's a liquid, let's say 45 degrees, it's also going to rise up. But somewhere along the line, it's going to condense and drip back into the flask. And only the one that vaporizes at 40 degrees will the vapor be able to enter the tube of the Liebig condenser. The liquid will be condensed and it can be caught up. Now, this is actually a very long process to remove the different fractions from the mixture. In the petrochemical industry, they have a more complicated fractioning column. And oh, seriously. Okay, let's just leave it at that. We have a setup known as a fractioning column. And all that happens is, over here is a container in which the crude oil is pumped into it. It's heated, and everything vaporizes. All right? Then it's allowed to enter this column, this chamber, the fractioning column. And we find substances with the lowest boiling point, in other words, those that would normally be gases at room temperature, for example, the gas that they use for gas stoves, all right, they rise right up to the top of the fractioning column. They don't want to condense because at room temperature, they are still gases, and they are caught up as gas, then refinery bottled gas. We use it for cooking on stoves. I think that's the most common one. The laboratory Bunsen burners work with gas from there. Then we find that the liquids with the next highest boiling points, 40 to 205 degrees, they will condense over here, and they are tapped off over there. Simultaneously, those with a higher boiling point taps off on the next level, and the next level, and the next level, and the next level. So in one go, they can separate out 1, 2, 3, 4, 5, 6, 7, 8 different fractions. All right. This is how they separate the different parts of crude oil. If you think about petrol and diesel, if you had to compare the two, petrol evaporates. Does diesel evaporate? No, not really. Why not? Because petrol has a boiling point between 40 and higher than that, all right? While diesel is over here between 250 and 350. So diesel is stickier, doesn't want to evaporate very easily. The forces holding the particles together are stronger than in petrol. That is why petrol has a lower boiling point. Yeah, that is why you keep your petrol tank sealed shut, because it wants to start vaporizing at those temperatures. All right. I don't think it's exactly 40, but I think it's probably nearby. Petrol is also a mixture. It contains molecules of, I think, approximately 6 carbons to about 12 carbons in the chain. All right. And the 6 carbon one will evaporate easier than the 12 carbon chain. All right. Diesel and these fuels are much longer molecules, much bigger molecules, so they are heavier. It's more difficult to make them evaporate or then cause them to boil. Okay, so the fractioning column, what is very important is the increase in boiling point. Those with the lowest boiling points, in other words, those that are normally gases, will come off right at the top. Those with the higher boiling points come down at the bottom. Here you will see diesel, lubricating oil, fuel oil. And right at the bottom of the fractioning column, there's a residue containing, among other things, bitumen. And we use bitumen for building. Bitumen is another name for tar. Okay. They use that in a road building. So in the petrochemical industry, all the fractions are used. Now, we'll come back to this fractional distillation of crude oil specifically when we do organic chemistry. Okay, and that would be a little bit later on in the syllabus. All right. Now, I just want to go back one. Fractional distillation. Okay, applications of distillation. Why do we use distillation in a laboratory? So that we can have, for assurance, so that you can test to see whether the stuff is pure or is what it has to be, because remember, pure substances have fixed boiling points, so you heat it up to that boiling point, and you can check the liquid that comes off. It should be that one done. Water purification, if you go and buy a bottle of distilled water, I don't know if some of your car batteries still are those with the little caps that you screw open, and you have to add a bit of water. You used to have to add distilled water to it. All right, now distilled water, I explained to you yesterday, they vaporize the water and condense it. All the salts and impurities will be left behind, for example, in steam irons. And where else? Desalination plants. The coast of Swakopmund, there's a desalination plant. They remove the salt from the seawater so that it can be used for good for human consumption. No. Okay. Alcoholic beverages. They do distillation. If you go and stand in front of a shelf, you can buy things called beer, malt, and wines. Then, in a different category, goes the so-called spirits, whiskey, brandy, whatever, okay? The spirits, they started out by fermenting the grapes or the malt and hops or whatever carbohydrate source they start off with. Then at a certain level, when there's a certain amount of alcohol in it, hereby 11, 12, 13%, the alcohol kills off the enzyme that does the fermentation. So what they go and do is to increase the alcoholic content, because if you go and look on a bottle of brandy, you'll see the alcoholic content is like 40% or 50% alcohol, while beer and wine vary from 3% to 11 or 12%. So by distilling the alcohol off from the fermented carbohydrate source, we can make whiskey and brandy and rum and any of the so-called spirits. They are usually also more expensive than just a bottle of wine. Okay. Perfume industry. They extract oils from plants and flowers. They don't do a normal distillation of the parts, but they extract it with a so-called steam distillation. They pass steam through it at fairly high temperatures, and then the oils dissolve in the steam, and from that then they can extract the oils, because the plant matter, etc., tends to want to burn at higher temperatures. And similarly, food flavorings, for example, citrus oil is also extracted by a steam distillation. You don't need to worry too much about that. All right, now, we have now had a look at filtration. We have had a look at distillation. Oh, and crystallization. So, filtration, crystallization, distillation. Now, the next way of extracting substances or separating mixtures from each other is something known as chromatography. All right? Big words. Lots of new words to go and learn. Chromatography. Now, chromatography separates different substances in a mixture because different substances have different solubilities. So what you're going to do is, this mixture is allowed to dissolve, for example, if it's water soluble, it dissolves in water. And then you draw the water up, for example, a column of sand or a paper, okay? And then we find that the least soluble substance gets left behind sooner, and the more soluble substance will move with the water or the solvent up through the paper. I have a picture of it. Over there, and it's much too. Now, here I have a picture of a chromatography process. You start off, you have either a container. Here we've got a rod onto which we've clamped a piece of paper. It's just a normal piece of filter paper, works very well. And then over here, on the filter paper, they've drawn a pencil line there. Okay. Why do we work with pencil? Pencil is not water soluble. Okay, because we're doing a water chromatography. Then on the piece of paper, they've marked a spot with a red Cokie or green ink and blue ink and black ink. And they leave it. The end of the paper is touching, or just slightly a millimeter or two into the water. And what is going to happen over here, we can see, can you see over there? The water has been drawn up through the paper. All right? And can you see the spots have moved? It no longer lies there. Why? Because the ink is water soluble. And it draws it up the chromatogram. A little while later, this is what we get. The spots have moved. We can see that the red ink that we started with is starting very slowly to separate there. You can see some yellow and there's some orange. Okay? The green ink we started out with very clearly contains yellow and blue. The blue ink contains blue and purple. And the black ink contains some yellow, there's some orange, there's some purple if you look carefully, if you're allowed to move further, and there is some blue. Do you follow me? So we can allow these substances to be pulled up through the chromatogram, and then when the water level reaches the top of the paper, you remove it from the water, because if you left it in there, the water is going to keep moving up and it's going to move all the spots right to the top of the paper. All right? So eventually you will get a piece of paper on which there are different color markings. And from that you can recognize, oh, my blue ink or my black ink contains blue. If you look at this chromatogram, the fact that this blue does not go up to the level of that blue, you can say it's not the same color blue. All right? Because the same pigment will have the same solubility and it will be carried up to the same level. You're all following me? All right. So we separate things because they have different solubilities. Now this is very simple. We can do this in class one day. We can try and do it this afternoon. If you've got some water-soluble Cokies, not permanent ones, we can give them a go. I think they are water-soluble. All right. We can do a couple of chromatograms. Okay. We'll use filter paper. This is probably filter paper. Okay. You get specialized chromatogram cards that's like a metal sheet, and on it is like a silicone powder that's like half dry on it. You can scratch it off with your finger. And then the solvent is sucked up or is drawn up through that silicone gel layer. You can do chromatograms with columns of sand, where the solvent will be drawn up the column of sand, or sometimes you can allow it to move down. The more soluble one moves the furthest, the least soluble one does not go as far. All right. Yeah, on the next picture, I've just done, it's actually upside down. The red pigment, can you see clearly, is breaking up into pink over here, and there's a bit of red over there. And what else? Some blue. Over here they've done one with a brown ink pen. Now we can do similar ones this afternoon. There's one with brown ink. Well, it seems as if there's some black over there. We have some pink over here and some, yes, but I think over here